Okay, so now that we have the basics of how we do Gaussian elimination down, we want to look at some of the properties of the solutions. And we're going to start off first of all by defining the inverse of a matrix. So we're going to say that if A is any n by n real matrix, notice that the inverse does not make sense if we're talking about a non-square matrix. And even though complex matrices do have inverses, we're only going to concentrate on real matrices in our work. We say that the matrix B is the inverse of A if and only if both the product of AB and BA is equal to the n by n identity matrix. Pretty standard definition. Notice that B has to be both a right hand and a left hand inverse of A in order to be the inverse of A. And of course we say therefore that B is the inverse of A, and we often say A is invertible, that's equivalent, and we're going to denote the inverse of A by A raised to the negative 1 power. Okay. Now, in these proofs that we're going to do, we're going to have to use some properties of homogeneous systems of equations. So first of all, what is a homogeneous system of equations? Well, it's basically any linear system where the right hand side, or that is the B vector, is equal to 0. Okay? And we're going to talk about a very special subset of Rn for an m by n coefficient matrix A called the kernel of A. And it's denoted thus. And it's defined as all of the solution vectors to the homogeneous system for that matrix A. So it's all the solutions of AX is equal to the 0 vector. Now there are some very important properties of homogeneous systems that we're going to use. The first is that you should realize that for any m by n matrix A, not necessarily a square matrix, its kernel is non-empty because the 0 vector is always in the kernel. And you can actually test that. Coefficient matrix times a 0 vector is always a 0 vector. Another important fact that it's true for homogeneous systems, not necessarily non-homogeneous, is that if the number of rows is less than the number of columns, the kernel has an infinite number of solutions. The last property is probably one of the most important, and it says that the solutions are closed under linear combinations. So in other words, if I take any two elements in the kernel of A, x sub 1 and x sub 2, any linear combination of those two vectors is also in the kernel of A. And you can verify that directly. That's an easy fact to verify. We're going to use these facts to prove 4 theorems now. The first theorem is going to tell us that for any linear system AX is equal to B, we either have 0, 1, or an infinite number of solutions. And we're going to prove this statement now. So first of all, it's very easy to construct systems that have 0 or 1 solution. So you can do that part. That's not hard to show. So we want to say, okay, suppose we have a linear system that doesn't have 0 or 1. We're going to show that as a consequence it has to have an infinite number of solutions. So if this system does not have 0 or 1 solutions, it has to have at least 2. Therefore, there exist 2 distinct vectors, x sub 1 and x sub 2, that are both solutions to our original linear system. Notice that their difference, x, is a non-zero vector, and it is a solution of the system AX is equal to 0. In other words, it's in the kernel of A. Now, we know that the kernel of A is closed under linear combinations, and one consequence of that is that if we take any element in the kernel of A and multiply it by a scalar, it's also in the kernel of A. So what this means is I can now construct a new vector x sub k, which is equal to x sub 1 plus k times x, where k is just some real number. And notice that k sub x, when A operates on it, gives us a 0 vector, and therefore all of these xk's are solutions to our original linear system. And you should verify that if it's not obvious. Now notice that these x sub k's are all distinct because x is a non-zero vector, and since there are an infinite number of real numbers k, there are an infinite number of these distinct solution vectors x sub k, from which we conclude that ax equal to b has an infinite number of solutions if it doesn't have 0 or 1 solution. And that proves our first theorem. Now, our second theorem has to do with when the system ax equal to b has a unique solution for every right-hand side vector b. And this theorem says that's true if and only if a is invertible. And we want to prove this statement now. Notice that in the hypothesis, A is an n by n real matrix. Okay, this is definitely not true if A is an m by n, where m is not equal to n. So let's look at the proof. Well, we have to prove this theorem both ways. So the forward proof would be to suppose that A is invertible and then show that for every b in Rn, Ax equal to b has exactly one solution. Okay. And showing that a solution exists is actually quite easy because A is invertible, so existence is not a problem, but uniqueness is something that we do have to prove. And so here we can use, and I'll leave this up to you as an exercise, and you should do this, show that if a solution exists, it has to be unique. And as a hint, we want to do something similar to what we did in the proof of theorem 1. Okay, we want to look at the kernel of A. Suppose two solutions exist and show that they have to be the same solution using what we know about the kernel of A. Okay, the backwards proof. And I just want to mention real quick that basically we're saying the solution is unique if and only if the kernel of the A only consists of the 0 vector. But I want you to prove uniqueness. It's a good proof to do for you. Okay, the backwards proof basically says that if Ax equal to b has a solution for every b, then A is invertible. And I want you to do this as an exercise. This is a constructive proof. I want you to show how you could construct the inverse of A knowing this fact. And I won't tell you anything beyond that. Okay, the third proof that we want to look at is talking about what the reduced row echelon form for an n by n matrix looks like. So if we have such an n by n matrix, we can say that one of two things are true about its reduced row echelon form. It's either the n by n identity matrix, or it has a row completely of zeros. And I'm going to sketch out the proof, but I want you to do it. The proof uses basically the definition of the reduced row echelon form of a matrix. So we're going to say, okay, suppose that it doesn't contain a row of zeros. Then we want to show that it has to be the identity matrix. And so we're going to say, okay, suppose that the kth element is not equal to 1. And I need a not equals to there, I'm sorry. Well, actually, we want to show that this is true, okay? I apologize. We want to show that the kth element of the reduced row echelon form of A has to be 1 for every k. And we're going to do that by contradiction. We're going to assume that it's not true and show using the definition of row echelon form that produces a contradiction. And so now once we know that the diagonal elements are all 1, we want to show that all the elements below it have to be 0. Okay. And that's obvious. That follows from row echelon form, okay? That's not hard. And then we want to show that all the elements above it are 0. And that follows from the definition of reduced row echelon form. So this is a good theorem to try to prove on your own, just to convince yourself that you have a good grasp of all the definitions. Okay, last thing we want to look at is probably the most important basic result in elementary linear algebra. And it says the following. It says if A is an n by n real matrix, the following statements are equivalent. probably the most important one in doing proofs is B, that the homogeneous solution has to be the trivial solution. Okay. And we haven't discussed determinants yet, so I'm not going to get too much into the last statement, but we can show that 1 through 5 are equivalent. And so I want to say a word about what it means to say statements are equivalent. Okay. So if we say that two statements are equivalent, in logic what that means is that if statement A is equivalent to B, it means that when A is true, that implies B is true, and when B is true, that implies A is true. Okay? And so this essentially means that A and B are the same thing. They basically mean the same thing. They're just different ways of saying it in a sense. And we write this as A if and only if B, which we sometimes use this notation of a double arrow, meaning that A implies B, but B implies A also. And in order to prove that two things are equivalent, we have to prove both directions hold. Given that A is true, it follows that B is true, and given that B is true, it follows that A is true. And then we've proved both directions of the implication. Now, how do we prove that a collection of statements are equivalent? This is different. We have a bunch of statements. Like in that last theorem, we have 5 different statements. And basically what we have to do is we have to be able to construct a graph or a path of if and only if statements that connect all of the statements. Okay. So if we want to prove the statements A, B, C, D, and E are equivalent, we have to construct a graph that connects all the statements. So this is one example, okay? In other words, given any one statement, I can get to the other statement, and of course backwards, okay? But there are other ways of doing it. I could, for example, prove the following, okay? And again, I can get to any other statement from any given statement, okay? So how are we going to do it? Well, we're going to do it the easiest way, okay? There's no one way that's proper or preferred. So we're going to show that the following are equivalent, and we use this TFAE as an abbreviation for the following are equivalent. This is the standard acronym in math. We're going to show these things are all equivalent. I'm going to prove some of these. Okay, so for example, if we look at this, we know that we already proved A is equivalent to E. That was theorem 2 actually. And I claim, and I'm going to leave this to you as an exercise, that you can show that B is equivalent to C. Okay? That AX equal to 0 only has a trivial solution if and only if the reduced row echelon of A is equal to the identity matrix. You should be able to show both directions. You can also show that C is equivalent to D. Okay? And last, we can show that A is equivalent to D. Okay? If it's invertible, it can be expressed as a product of elementary row operations. And you should convince yourself that knowing all of these statements are true allows us to connect them up in such a way that every statement is connected to every other statement with an if and only if statement, and therefore all of them are equivalent. Okay. And these are things that you should show. You should prove all of these things except A if and only if E, since we already proved that. Okay. Now we want to get into some properties of matrices after this.